Okay, thanks for the introduction, Jerome. My topic is decision referrals in human automation teams. So I'll give a brief introduction to human automation collaboration and review some of the related work, and also discuss some human factors which need to be considered in modeling such systems. Then I present our work, decision referrals in human automation teams, and then we'll discuss some directions for future work. So the basic motivation for human automation collaboration comes from the fact that automation and humans have different models of decision making. And even before that, automation has already entered the domains of both physical tasks and mental tasks. So mental tasks such as data analysis and decision making can be assisted through automated systems. So, and the basic premise here is that automation is good at the number crunching and repeatability of results. Humans are good at reasoning with quick mental models, which gives them advantage in new situations. So in collaborative decision making, both these strengths can be utilized. So let's look at some of the motivating applications across domains for this kind of a collaboration. So search and rescue missions come to mind. So imagine a search and rescue team is searching for a missing human, and they are being assisted with an automated system which skims through large amounts of data, such as video footage and also heat signatures and so on. So now the automation and the team themselves are also searching for the target or the missing human. So the automation needs to decide which chunk of data or which part of the footage that needs to be shown to the human. So the team should not be disturbed unnecessarily. So the automation has this trade-off of which data should be shown to the team and which need to be it should evaluate by itself. So some other applications can be found in reconnaissance and intelligence for defense purposes. So for identification of hostile targets and automated mine detection and so on. And also there are applications in other domains such as decision support systems in pharmacies and which assist healthcare professionals and so on. And also there has been some talk on AI being a member of boardroom, trying to provide assistance in risk assessment and decision making in finance and business. So the ideas for human resource collaboration come from different bodies of literature. So there has been work on distributed collaborative systems and distributed hypothesis testing for purely automated agents. So in distributed hypothesis testing, there are a set of agents, and each of which has partially informative observation, which is private to that agent, and they are trying to reach consensus on what is the true state of a certain environment. And you could say some of the ideas from hypothesis testing form the basis for our modeling. And there has been a lot of work on the impact of workload on human performance. We shall discuss some of this as we go along. More recently, there has been work on decision queues where the human is modeled as a server with utilization-dependent performance. And there have been some literature on task allocation, which is close to our model by Hume in 2015 and Dubois 2020. We shall discuss this also as we go along. So let's look at an application scenario. So this shows the simulation of a radar screen. There are a bunch of targets presented to a human operator on the screen. So if the when the human operator clicks on any of the target, the information here is displayed. So information such as weapons, identification response, distance, altitude, and so on. And the operator needs to decide whether the target is hostile or non-hostile. So when the number of targets is very large, the operator can be assisted with an automation which decides which subset of targets can be shown to the human being for review and final decision, and which targets can be completed by the automation itself. So in general, in human automation collaboration systems, these are the factors, some of the factors involved: cognitive workload, task load, fatigue, self-confidence, trust, and belief in automation. We shall only discuss the first two. So cognitive workload or mental workload. A notion of cognitive workload is needed to answer questions of practical importance, such as, in a given situation, how busy is an operator, how complex are the tasks that the operator needs to complete, and can the operator respond to unexpected events, and can he or she handle some additional tasks. So there are varied notions of cognitive workload or mental workload across literature, and the definitions are based on, they depend on the application, because that will determine the resources that are employed in the task, such as memory, attention, and so on. So here is a comment from a study by NASA. So low workload levels have been associated with boredom and decreased attention to the task, whereas high workload levels have been associated with increased error rates and narrowing of attention. So as you can see, this is the cognitive workload is a complex construct. So how is it assessed? Usually through feedback from human operators. So different scales are used, and there are different set of questionnaires have been set up. So commonly used scales are Bedford scale and NASA TLX. So the Bedford scale is a unidimensional scale. So it tries to map the operator's mental capacity, spare mental capacity, to a 10-point scale. On the other hand, NASA TLX is a multidimensional scale, which looks at a lot more dimensions, such as mental demand, physical demand, temporal demand. Temporal demand here is means, does the operator feel rushed or in a hurry while completing the task? And here, this is a effort here. Effort and performance here refer to the self-appraisal feedback of the operator, frustration level. So we look at some of the commonly asked questions. So the questionnaire would look something like this. So how mentally demanding was the task? Physically demanding? Was it hurried or rushed? How successful? So this is a self-appraisal question. So how successful were you in accomplished what you were asked to do? And how hard did they feel? to perform at that level. And this is about the frustration level. So each of these scales is between very low and very high, very low, medium, and very high. So there are 21 points. So this is a multi-dimensional scale, which is very diagnostic. And this is a very commonly used scale. We, on the other hand, will not focus on cognitive workload. We will focus on what we call task load or simply workload. So because we have seen that cognitive workload is a very complex construct, task load, on the other hand, it can be defined as the number of tasks per session or number of tasks from a given batch of tasks assigned to the human. So cognitive workload can be a function of task load along with other variables. So cognitive workload here is essentially the system state, which is not directly observable, while task load is the control variable. So we shall see what assumptions we make about this relationship. So in the literature on task allocation planning, so the models can be classified into different categories. So human as interventionist and human as non-interventionist, they are based on the behavior of the human in the model. So human as interventionist, so human can redo some of the tasks that have already been completed by the automation. For example, if there is some task, some classification task, the human, because he or she does not trust the automation enough or something like that, depending on its cognitive state, he can redo some of the tasks already completed. And the human may interrupt tasks of the robot. This is also there in some of the models. The human as non-interventionist, in this case, the human does not intervene with the robot's task, but he or she may or may not adhere to the assigned workload. And this blind task allocation and informed task allocation are categories based on the task allocation strategy. In blind task allocation, the decision maker does not look at the tasks before allocation. So the task assignment happens based on the estimated cognitive state of the human or the expected performance of the human. So the decision maker has some model or metric for the performance of the human and some estimated cognitive states. The allocation is done based on that rather than looking at each of the tasks. So this is blind task allocation. Informed task allocation is where the decision maker, in this case the automation, looks at each task before deciding whether it needs to be sent to the human. Our work falls into this category. So let us discuss one of the works, which recent works with task allocation with human intervention. So let's discuss Dubois and Lenny 2020. So in this work, there is a human automation team which is presented with batches of classification tasks sequentially. And the automation suggests a fraction of tasks to be carried out by the human. Here, the human's performance is a function of workload or task load. Remember, this is not cognitive workload. This is just the fraction of tasks in the batch. So the human completes these tasks, and then based on the cognitive state of the human, he or she may take up more tasks. So now, this might, if the human takes more tasks, this might impact the performance of the classification performance of the human adversely. So This based on the trust level of the human, he takes up more tasks, or so the automation needs to consider this fact and decide on what fraction of tasks it needs to give the human, so that so that the long-term performance is maximized. So they propose a POMDB-based approach based on an autoregressive model for the cognitive state. So in our case, we do not have this cognitive state represented explicitly in our model, but notice that there is this falls under the blind task allocation category because they do not differentiate between the tasks that are being allocated. So coming to our current work, so decision referrals in human automation teams. So this is the setup. So the human automation team is presented with binary classification tasks, and there is a hierarchical structure. The automation first looks at the batch of tasks, and it decides a subset n of the tasks that need to be given to the human, and the human reviews the tasks and takes the final decision. So, and all the other tasks are completed by the automation. So broadly, the problem statement would be, given a batch of binary classification tasks, what is the optimal subset of tasks that must be referred to the human? So again, it's from this application scenario, which subset of targets needs to be shown to the human. So if we have the system model, so a batch of k IID binary classification tasks. So each task can be from two hypotheses, H0 or H1. So in our application, that would be non-hostile or hostile. And the tasks are, and the states are IID across tasks. For the same task, the automation and the human have different observation values. So Y1 is the observation space of the automation, Y2 is the observation space of the human. So observations are essentially random variables which depend on the true state. So for example, in our case, it would be the case that hostile targets might be moving at a higher velocity than non-hostile targets, and so on for different. Similarly for speed and so on for different parameters. So the observations are IID across tasks, but they are dependent on the states. One simple observation model for the automation's observation. So the automation's observation model is static, meaning it doesn't change with task load. One example model is the additive white Gaussian noise channel, where here HK represents the hypothesis, and N is a noise factor with known mean and variance. On the other hand, the observation model of the human is workload dependent. So here workload here is defined as the fraction of tasks from the batch of tasks presented. So the human the performance of the human decreases with workload. This can be represented by the following model: an AWGN channel with workload dependent variance. So HN here is the true hypothesis, and this is a noise factor whose variance is a function of workload. You can have other models also, such as the mean can be a function of a workload, and a hybrid model where the mean and the variance both are a function of workload. So these are the underlying assumptions of about the human's decision model. So for each task, the human decides between the hypothesis based on only his or her own observation. So he does not he does not have access to the automation's observation. So this is justifiable because the automation might be, for example, if the automation is using some kind of a neural network to make the classification decision, and the human might not be able to interpret the functional state of the automation. So the human does not does not account for the fact that the automation has looked at the task and then referred it to him. So he discards that information and freshly looks at the task. So one more underlying assumption is that the human is active and pays attention to tasks at all workloads. So because as we had previously seen that in the comment from the NASA study, lower workloads are associated with boredom and less attention towards the tasks. So if the human is not paying attention to the task, they will, and just monitoring the automation, they are not a part of the active control group. So here we assume that the human is active and pays attention to the tasks at all workloads. So from this we can say that with at higher workloads there is lower performance, or else the case would arise that at very low workloads there would be also lower performance. But in our case, in our model, that is not the case. Performance degrades with workload. More on human decision model. So as we are looking at a classification problem, the human's classification capability is characterized by two values. So for each workload, value of workload W, the true positive rate and the false positive rate characterize the performance of the human. True positive rate and false positive rate, or equivalently misdetection and false alarm rates can also be used. And the automation does not know the human's decision model exactly. It only knows these values, the true positive rate and false positive rate for each workload level. Coming to the problem formulation, we pose this as a cost minimization problem. So costs are associated with every decision. So there are classification costs. So classification costs depend upon the decision, the classification choice made by the decision maker and the actual state. So if the HK is the true state and DK is the decision made by the decision maker, in the sense here the team. So if DK is equal, if HK is equal to H1 and DK is equal to H1, so we call that true positive. Similarly, the errors here would be like false positive and false negative. False positive is what is generally called as false alarm, and false negative is the missed detection. So the values of these costs depend on application. For example, misdetection cost of misdetection might be greater than the false alarm cost in some defense scenarios, because misdetection might cause death and destruction. False alarm might not be costly. I'm just imagining such a scenario, but our formulation is general. So we talked about classification costs. Now we talk about referral decision costs. So when the automation refers a task to the human, there is an additional cost for every referral. And in addition, so the referral decision cost of a task would be the classification cost of the human plus the additional cost. So if for a subset n, the total referral decision cost would be the total additional cost of referral plus the total expected classification cost of the human from the perspective of the automation. So this will be a function of the expected performance of the human, the true positive and false positive rates, which are known to the automation. Now the problem is, given a set of posterior beliefs, so the tasks here are represented by posterior beliefs of the automation, given a set of k tasks represented by the posterior beliefs, and the performance metrics of the human, determine the subset of tasks n and the classification decisions such that the total cost is minimized. So here the total cost would be cost of the classification decision of the automation and cost of the classification decision of the human plus the additional cost, sorry, that is missing, plus the additional cost of referring the tasks. So these costs are computed from the perspective of the automation. So for example, here the human classification cost is linear in posterior belief of the that the task is hypothesis 0 or hypothesis 1, which is computed by the automation. Now coming to the, we present an optimal decision reference scheme. So the way we proceed to do that is, for each task k, we define an index which we call the G index. G index for task k under workload W is defined as follows. C1 bar here is the cost incurred if the automation completes the task, and gamma 2 bar is the classification decision cost of the human, and this is the additional cost. So essentially the G index of task k is the cost reduced by referring it to the human, essentially, and it is a function of the workload. So we have a result here which says that for a fixed workload W, it is optimal to allocate the tasks with highest G indices to the human. So now this result is true for a fixed workload W, and then using this result, we want to find the optimal workload W star and also the corresponding allocation. So the total expected cost is equivalent. Finding the total, the minimum expected cost is equivalent to minimizing the decision, the referral costs, which is a function of workload. So the optimal workload can be found by evaluating G bar of n for all possible workload values. So this can be done for, let's say, if k is equal to 50, there are 51 possibilities, so you can easily search over them. So that gives you the optimal referral scheme. Let's look at an example, numerical example, which illustrates this problem. So here the x-axis shows the posterior belief about a task, and y-axis the decision classification cost. So each task is a point on the x-axis. So if you have k tasks, k is equal to 20, that would mean each task is represented by the one point on this x-axis. So the tasks are scattered along this axis. Here the red line is the classification decision cost of the automation, and the blue lines are the expected classification cost of the human as function of workload. So the lowest line here corresponds to 1 task out of 20, 2 tasks out of 20 allocated to the human, and so on. So now, given a set of k tasks, which are points on this axis, which is the workload level you would choose? And which subset of them would be given to the human is the problem. So here, if you fix the workload level, so if you choose one of the line here, there would be 2 thresholds. So if your posterior belief falls between those thresholds, the cost of offloading it to or referring it to human is less than the cost of the automation completing the tasks by itself. So the problem boils down to what is the which line do we want to choose? So we compare our optimal policy to 2 baseline policies. One is the blind allocation, which decides on a workload which uses a static workload and assigns randomly. This static workload is based on the expected performance of the human. Static allocation is a heuristic which also uses constant workload, but if it refers the tasks in an informed manner according to our lemma. So if you recall our lemma, it says that under fixed workload, you have to compute the G index for each task and allocate it in an descending order of the G index. That is, and that would be an optimal for that workload value. So static allocation fixes a workload and it allocates based on lemma 1. Let's look at some simulation results. So here the square is the blind allocation scheme. So this is for different problem instances. A problem instance is defined based on if you specify the observation models and the costs, decision costs, you define a problem instance. So this is across 25 problem instances. So you can see that the blind allocation policy has a much higher cost than the informed allocation policies, which look at the tasks before referring them to the human. And here this is a very standard deviation of the cost, and the blind allocation policy has higher variance of higher standard deviation also. Here we show the average workload allotted to the human across different problem instances. So because the blind allocation and static allocation are assigned the same workload, there is no variation. You can see that blind allocation sometimes allocates very less workload to the human because it does not look at the tasks. So the conclusion for now is that informed allocation policies are better than static and blind allocation policies, and informed allocation heuristics which are close to optimal can be devised based on the convenience of implementation. We plan to validate this model through experiments with human participants, and also include factors such as trust, belief in the automation in our model later on. This work has been published recently in IEEE CDC, and these are some of the references. So this reference by Wickens, Holland, Danbury, and Parshuraman is one of the primary textbooks for this area. If interested, you can look at it. And thank you for listening.